Welcome to this lecture on predictive analysis in big data. Over the next slides, we'll explore how historical records, statistical methods, and machine learning combine to reveal future trends and actionable forecasts. I'll guide you through the core concepts, the data pipeline, modeling choices, and real-world applications, so you can see how predictive insights turn raw information into repeatable business value. At the heart of predictive analysis are three pillars: clean historical data that removes noise and captures behavior, robust statistical algorithms that identify patterns and quantify relationships, and machine learning loops that continuously refine models as new data arrives. Together, these elements move us from raw records to actionable forecasts, forming a repeatable process for strategic decision-making. Big data delivers value through scale, speed, and diversity. Massive petabyte inputs supply stable examples and reveal subtle patterns. Real-time scoring enables immediate decisions by separating signal from noise, and varied data sources reduce blind spots across seasons, channels, and customer segments. When combined, these dimensions sustain predictive power and help models generalize across changing business conditions. A reliable predictive pipeline starts with ingestion of multi-source logs and sensor feeds, then cleaning to unify formats and handle missing values, followed by exploration to find trends and candidate predictors. Feature engineering turns insights into measurable variables for modeling, and governance tracks lineage and quality. Continuous monitoring and iteration keep models aligned with evolving data and business needs. Linear and logistic regression provide foundational predictive capabilities with clear interpretability. Linear models estimate continuous outcomes like next quarter sales and support revenue forecasting, while logistic models estimate event probabilities such as churn risk for classification tasks. Both serve as transparent baselines that quantify variable impact, making them useful benchmarks before moving to more complex learners. Advanced models handle high-capacity, nonlinear interactions. Ensemble methods like random forests and gradient boosting average many weak trees to reduce overfitting and improve accuracy, while neural networks use hidden layers to detect intricate patterns when parameters scale into the millions. Choosing these techniques requires balancing interpretability against precision depending on problem complexity and operational needs. Time series forecasting separates trend, seasonality, and residuals to produce reliable forecasts for inventory, energy, and staffing needs, using techniques like ARIMA and exponential smoothing. On the other side, segmentation and clustering methods such as k-means and db-scan turn unstructured customer or device data into behavioral cohorts, enabling targeted campaigns, improved personalization, and anomaly detection for sharper decision-making. Evaluating models means ensuring generalization and aligning metrics with business impact. Split data into training, validation, and test sets for robust tuning, and choose metrics like RMSE or MAPE for continuous forecasts, and AUC or F1 for classification depending on cost of errors. Complement this with cross-validation, back-testing, and residual diagnostics to detect bias and confirm model stability over time. Deploying models requires integration into real-time scoring, scheduled batch pipelines, or embedded outputs in dashboards and workflows, while automation triggers downstream actions. Continuous monitoring compares predicted versus actual outcomes, raises alerts on performance decay, and initiates retraining when drift is detected, creating a closed loop that preserves accuracy and aligns models with market evolution. Predictive analysis delivers measurable ROI across industries by turning model outputs into operational gains. In retail, forecasts optimize inventory and reduce stockouts. In banking, credit risk models reduce defaults and support revenue growth. Utilities use consumption predictions to balance loads and improve grid efficiency. These examples show how analytics projects scale into core operations and generate sustained returns. Ethical AI practices safeguard trust while enabling innovation. Transparent documentation, bias audits, and compliance measures protect reputation and meet regulations, while anonymization access controls, and explainable techniques build consumer trust. Embedding these safeguards early ensures predictive systems are accountable and sustainable, allowing organizations to leverage predictive power as a long-term competitive advantage. A strategic framework for predictive insights is iterative and cross-functional. Start by selecting high-value use cases and building interpretable baseline models, then progressively add complexity as needed. Foster collaboration between domain experts, data engineers, and analysts, continuously refine features and models, and embed insights into daily decisions so analytics compounds into long-term operational improvements.